Welcome, truth seekers. Have you ever looked up at the night sky and wondered how ancient scholars long before satellites or telescopes could chart the stars with such astonishing accuracy? No computers, no precision optics, just ink, intellect, and the vast heavens above. In the heart of the Islamic Golden Age, while Europe was still struggling to emerge from centuries of stagnation, Muslim astronomers were building observatories, inventing instruments, and challenging everything humanity thought it knew about the cosmos. From the sands of Khorasan to the domes of Damascus, they were deciphering the movements of planets, solving complex mathematical equations, and sketching celestial maps that would later inspire the likes of Copernicus and Galileo. But here's the real mystery. How did these minds like Al-Biruni, Al-Tusi, and Ibn al-Shatir manage to predict planetary alignments and stellar positions with such eerie precision? Some of their calculations were so advanced, modern historians are still piecing together how they were even made. And buried within their work is something even more intriguing, a bridge between astronomy and astrology, science and the soul. Did they see the stars as distant objects or divine messengers? Grab your coffee and enjoy the story. Welcome to Unleash Facts, the place where history secrets, unsolved mysteries, and mind-blowing truths come to light. In the 8th century, something extraordinary began to unfold across the Islamic world. While much of Europe remained cloaked in superstition and political turmoil, the Islamic Empire stretched from the Atlantic shores of Spain to the edges of India. And within this vast territory, a remarkable transformation was taking place. Mathematics, philosophy, medicine, and astronomy were not just preserved, they were elevated, refined, and pushed far beyond what the Greeks and Persians had ever imagined. But why astronomy? Why did Muslim scholars fix their eyes on the stars with such devotion? The answer lies in a blend of faith, necessity, and an unquenchable thirst for knowledge. The Islamic prayer calendar demanded precise knowledge of the lunar cycle. Ramadan began with the sighting of the crescent moon. Daily prayers had to align with the sun's position in the sky. And the Qibla, the sacred direction Muslims face during prayer, required accurate geographic orientation. In short, religion demanded astronomy. But faith wasn't the only motivator. Under Abbasid caliphs like Al-Mun, science became a political tool, a way to unify a diverse empire through knowledge. Al-Mun, fascinated by Greek philosophy and science, established the legendary House of Wisdom in Baghdad. It became the intellectual nucleus of the Islamic world. Here, scholars translated ancient Greek texts, but more importantly, they expanded upon them. They didn't just copy Ptolemy, they corrected him. Observatories began to rise in places like Baghdad, Ray, and later Moraga. These weren't just buildings, they were temples of inquiry, armed with instruments designed to measure the sky with terrifying precision. The Astrolabe, perfected by Muslim minds, became a kind of analog computer. With it, one could tell time, find the Qibla, calculate prayer times, and even navigate across deserts and seas. And these weren't isolated pockets of brilliance. This was a civilization-wide obsession. The thirst for understanding the cosmos was woven into every level of society. Students traveled hundreds of miles to study under master astronomers. Wealthy patrons funded observatories and offered prizes for accurate models of the planets. It was a world where genius didn't have to fight for attention. It was celebrated, nourished, and recorded in books that would later travel to Europe and quietly ignite a revolution. And perhaps the most curious part of all? Many of these scholars saw no contradiction between astronomy and astrology. To them, the stars weren't just distant balls of gas. They were signs, patterns, maybe even whispers from a deeper order of existence. They measured their movements, yes, but they also wondered about their meaning. So how did this era produce minds sharp enough to rival even modern astronomers? How did one of them, Al-Biruni, calculate the Earth's radius with stunning accuracy without ever leaving his region? That's where we're headed next. The journey into genius is just beginning. Imagine trying to measure the size of the Earth without ever traveling around it. No satellites, no airplanes, not even a compass as we know it today. Just a mountain, a little trigonometry, and a man whose mind was centuries ahead of his time. That man was Abu Rayyan al-Biruni. Born in the year 973 in Khwarazm, modern-day Uzbekistan, al-Biruni was not merely an astronomer. He was a polymath in the truest sense of the word. Mathematics, physics, geology, pharmacology, even comparative religion. His curiosity had no limits. But it was his passion for astronomy that earned him a place among the great minds of human history. Now here's where it gets astonishing. Using nothing more than observations from a single mountain and basic trigonometric calculations, Al-Biruni estimated the Earth's radius to be 6,339.6 kilometers. Today's modern measurement? Roughly 6,371 kilometers. That's a difference of just 31 kilometers. Let that sink in. Over 1,000 years ago, a man without a telescope or satellite data got it nearly perfect. But Al-Biruni didn't stop there. He wrote a massive compendium on astronomy called Al-Qanun al-Masudi, where he detailed hundreds of astronomical observations, planetary positions, and corrections to Ptolemaic models. He was obsessed with precision. He cataloged over 100 different star positions. He even discussed the possibility that the Earth rotated on its axis, a theory that would not be widely accepted in Europe until centuries later. And then there's the part that still puzzles historians. How did he achieve such refined results with such limited instruments? His tools were mostly analog sundials, quadrants, astrolabes. No lenses, no advanced optics. Yet somehow, his calculations were so accurate, they've been verified using modern technology. It's as if he had access to knowledge that shouldn't have existed yet. His deep grasp of mathematics and geometry wasn't just academic, it was functional. He used it to build models of the solar system, track lunar and solar eclipses, and even correct the Islamic calendar. But perhaps what's most impressive was his scientific integrity. Al-Biruni famously criticized astrologers who made wild predictions without evidence. He believed that understanding the heavens required reason, not superstition. And yet, he never entirely dismissed the symbolic power of the stars. He recognized the psychological pull of astrology, and while he rejected its baseless claims, he acknowledged its cultural value. In this, Al-Biruni was a bridge scientist with a spiritual awareness, balancing logic and legacy. But he wasn't alone in this intellectual awakening. A few centuries later, another brilliant figure would take the study of planetary motion to a level that would echo directly into the heart of the European Renaissance. His name? Nasir al-Din al-Tusi. And what he discovered would leave even Galileo speechless. Step into the windswept hills of 13th century Persia. There, perched high above the plains in the city of Maragha, stands a structure unlike anything the Islamic world had ever seen. It's not a palace. It's not a mosque. It's an observatory massive, meticulously designed and built for one purpose: to decode the language of the stars. At the heart of this scientific marvel was Nasir al-Din al-Tusi, one of the greatest astronomers and mathematicians the world has ever known. Born in 1201 during a time of political chaos, Al-Tusi's early life was shadowed by war, including the Mongol invasions. But through resilience and brilliance, he managed to rise, not just as a scholar, but as a force that would quietly reshape our understanding of planetary motion. Al-Tusi's greatest legacy? A geometric breakthrough known today as the Tusi couple. Sounds simple, right? It's anything but. Picture this: two circles, one rolling inside the other, producing a straight line motion from entirely circular paths. With this mechanism, Al-Tusi solved the problem that had haunted astronomers since Ptolemy: how to model linear planetary motion using only circles, without violating the long-held Aristotelian belief that celestial bodies must move in perfect circles. And here's where it gets really interesting. Centuries later, Nicolaus Copernicus, the father of the heliocentric model, used the exact same mathematical device in his own planetary models, but there's no record of how he learned it. The Tusi couple never existed in Greek science. It emerged in Moraga, deep within the Islamic world. So the question lingers, did Copernicus have access to these Islamic texts? Was the scientific revolution in Europe built, quietly and invisibly, on the shoulders of Persian genius? Back in Moraga, Al-Tusi didn't work alone. The observatory functioned more like a scientific institute, employing dozens of astronomers and mathematicians. Together, they charted the stars with uncanny precision, built massive instruments to track celestial motion, and compiled star catalogs that would later ripple across continents. They were driven by more than curiosity. Like Al-Biruni before him, Al-Tusi worked to fix the Islamic calendar, refine astronomical tables, and improve navigation. But he also sought to reconcile reason with belief. Al-Tusi was a theologian, a philosopher, and a scientist all at once. He saw the universe not as a cold machine, but as a structured harmony, waiting to be understood through logic and observation. And that harmony extended to the instruments they used. Imagine a giant armillary sphere, bigger than a man. Imagine giant mural quadrants carved into the very walls of the observatory, so that shadows from the stars could be measured down to fractions of a degree. These tools weren't just impressive, they were revolutionary. They allowed Al-Tusi and his team to track planetary anomalies, identify errors in Ptolemaic theory, and hint just faintly at a universe where Earth might not be the center of it all. But Al-Tusi wouldn't be the one to break that barrier completely. That task would fall to a man who lived just before Copernicus, a man whose planetary models would come so close to heliocentrism, it's almost eerie. His name, Ibn al-Shatir, and what he accomplished next would change everything. Now, let's move to 14th century Damascus, a city bustling with scholars, poets, artisans, and beneath its skies, one man with a mind sharp enough to rival Copernicus himself. His name was Ibn al-Shatir, and what he drew on parchment in the 1350s would shake the foundations of astronomy if only the world had listened. Unlike many scholars of his era, Ibn al-Shatir wasn't nestled in a royal observatory or funded by a caliph. He was the Muwaqqit, the official timekeeper of the Umayyad Mosque. His job was simple in appearance: calculate prayer times with utmost precision. But that task required him to study the sun's position, the movement of the moon, and the paths of stars across the heavens. And from that humble responsibility came a revolution. Ibn al-Shatir was dissatisfied with the ancient models passed down from Ptolemy. Like Al-Tusi, he knew something was wrong with the idea of epicycles and deference, the tangled loops that Ptolemaic astronomy used to explain planetary motion. So he did what few dared to do. He scrapped the Ptolemaic system and rebuilt it from the ground up. His solution? A completely new planetary model, one that eliminated the equant, the awkward placeholder Ptolemy used to explain uneven planetary speeds. Instead, Ibn al-Shatir created geometric models that mimicked real planetary motion far more accurately. His system still kept the Earth at the center, but the mechanics were astonishingly close to what Copernicus would later propose. And here's where things get mysterious. The mathematical diagrams Copernicus used in De Revolutionibus are in several cases nearly identical to Ibn al-Shatir's, down to the structure of the epicycles. But Copernicus never credited any Muslim astronomer. So how did these models travel from Damascus to Renaissance Europe? Some historians suggest the answer lies in translation. Islamic manuscripts had been making their way into European libraries through Sicily, Spain, and even Byzantium, where cross-cultural exchanges were more common than we like to admit. Could a monk or scholar have translated Ibn al-Shatir's work, only for it to be absorbed quietly into the European canon? But here's what can't be denied. Ibn al-Shatir's models worked. He predicted planetary positions with remarkable accuracy. His lunar theory, in particular, was closer to modern models than anything that came before him. He built advanced sundials and astronomical instruments, many of which influenced the design of timekeeping tools used across the Ottoman Empire and beyond. Yet, in the Western historical narrative, his name is barely mentioned. His diagrams are there. His math is there. But the man himself? Erased by time, or perhaps buried under the politics of scientific pride. Still, his legacy remains in the stars' quiet, uncredited, but real. And that raises a deeper question. How much of what we call European discovery was actually seeded by Eastern minds working centuries earlier? As we dive deeper, we'll uncover how Muslim astronomers didn't just look to the stars for science, but also for meaning-blending astronomy with the ancient mystical language of astrology. Not superstition, not mere symbolism, but a system of interpretation that once guided empires. And perhaps, just perhaps, still lingers in ways we don't fully understand. In today's world, we draw a hard line between science and mysticism. Astronomy's precision, data, math, astrology, often brushed off as superstition or entertainment. But in the Islamic Golden Age, that line wasn't so clear. To many of the greatest minds of the era, the stars were more than just distant suns. They were symbols, signals, keys to understanding both the cosmos and the soul. It's important to understand that Islamic scholars didn't approach astrology blindly. They knew the difference between empirical observation and speculative belief. But they also lived in a time when celestial movement was deeply intertwined with earthly events. The heavens weren't passive. They were a clock, a map, and possibly a mirror reflecting divine will. Caliphs, sultans, and viziers often consulted astrologers before major decisions, wars, marriages, even the founding of cities. Baghdad, for instance, was established with astrologers choosing the precise date based on planetary alignments. Coincidence? Not to them. The position of Saturn, Jupiter, and Mars had meaning. The moon's cycle wasn't just about tides, it was tied to fate. But here's what makes this fascinating. The same scholars who built observatories and refined trigonometry were also studying birth charts and planetary conjunctions. Al-Biruni himself wrote a detailed critique of astrology, not to dismiss it entirely, but to separate its credible aspects from its more absurd claims. He believed in the influence of celestial bodies, but demanded logic, evidence, and structure. In a way, he was trying to elevate astrology into a science. Al-Tusi explored the relationship between the soul and the stars. He theorized about celestial harmonies, drawing from Greek Neoplatonism and Islamic philosophy. To him, the cosmos was not just physical, it was metaphysical. A layered structure that echoed divine order, where every movement above had an echo below. And then there were the instruments. The Astrolabe, often seen as an astronomer's tool, was also used by astrologers to cast horoscopes. With it, they calculated the ascendant, the position of planets at the moment of birth, and used complex mathematical tables to interpret their significance. This wasn't guesswork, it was calculation, geometry, and timing. What makes this so compelling is the duality. These scholars weren't choosing between science and mysticism. They were pursuing both. They believed that the universe operated on laws, divine laws, and that to understand those laws was to come closer to the truth, whether it came through a telescope or a chart of the zodiac. But here's the twist. Their work didn't stay locked in the East. It traveled. Through translations, their texts reached Europe, where the same ideas took root, sometimes altered, sometimes hidden, often uncredited. Astrological diagrams in medieval European manuscripts bear striking resemblance to Islamic sources. And Renaissance thinkers like Kepler and even Newton studied astrology alongside physics. So the question remains, did these scholars believe the stars controlled destiny? Or were they merely reading the patterns of a divine machine, trying to understand a code written in the sky? Either way, the result is undeniable. Through their blend of astronomy and astrology, reason and symbolism, they opened a path for others to follow. And when Europe finally began to awaken from its slumber, it unknowingly stepped onto a road paved by Muslim hands. So how this vast body of knowledge made its way to the West, often stripped of its origins, and silently shaped the so-called scientific revolution. And more importantly, why the legacy of these forgotten minds still matters today. By the time the Renaissance flared to life in Europe, its scholars spoke of bold discoveries, radical theories, and a new vision of the universe. Copernicus placed the sun at the center. Galileo turned telescopes toward the skies. Kepler charted the elliptical orbits of planets. Newton revealed the laws of motion. It seemed like a sudden leap, an explosion of brilliance out of nowhere. But was it really? Behind those famous names lies a quieter truth. A centuries-old stream of knowledge had already been flowing, carried through translated texts, preserved manuscripts, and forgotten diagrams. Many of the breakthroughs we now associate with Europe were, in fact, rooted in the observatories of Moraga, the books of Al-Biruni, and the models of Ibn al-Shatir. In Spain, Sicily, and Constantinople, Muslim manuscripts were translated into Latin, sometimes openly, sometimes anonymously. Astronomical tables, planetary models, and mathematical treatises crossed borders and centuries. Scholars like Gerard of Cremona and Michael Scott translated works from Arabic into Latin, unknowingly embedding Islamic genius into the foundations of the Western scientific canon. Even the language of science reveals the debt. Words like zenith, azimuth, algebra, and algorithm all trace their roots back to Arabic. But the deeper concepts, the geometrical models, the critical evaluation of Ptolemaic astronomy, the trigonometric methods, those influences were absorbed silently, rarely credited, often repackaged, and over time the trail vanished. Copernicus's planetary diagrams mirror Ibn al-Shatir's. His mathematical tool, the Tusi couple, emerges first in Persian manuscripts. Al-Biruni's measurements prefigure modern geodesy, and yet their names are often footnotes, if mentioned at all. It's not conspiracy, it's cultural erosion, a byproduct of power, empire, and narrative control. But this isn't just about credit, it's about continuity. The so-called scientific revolution wasn't a rebirth, it was a relay. A torch passed silently across time zones, cultures, and languages. The Muslim astronomers didn't merely preserve Greek knowledge, they questioned it, corrected it, expanded it. They treated the cosmos as both sacred and solvable. And now, in an age where machines orbit planets and telescopes peer into distant galaxies, it's easy to forget the quiet figures who once climbed rooftops with wooden instruments and parchment charts. Scholars who stared into the same stars we see today and asked the same questions. How does it all move? What holds it together? And perhaps most haunting of all, is there meaning in the motion? Today, their legacy lives on in observatories, star charts, and the very framework of modern science. Not as monuments of the past, but as reminders that truth often travels farther than we think, and doesn't always arrive wearing its original name. Thanks for watching, and see you in the next one.